You have never seen a broken glass leap off the floor, reassemble itself in midair, and land gracefully back on the counter. You have never watched a candle suck melted wax back into its wick, or heard your birthday song play backward in real life. These are the kinds of everyday miracles that simply never happen. Not because the universe is boring, but because it has rules. And one of its most deeply ingrained rules is this: time does not reverse. It has a direction, a flow, a sense of before and after that everything in existence obeys without question. It is strange, though. If you think about it, most of the basic laws of physics do not actually care which way time moves. Newton's equations, for instance, would work just fine if you rewound them. If you threw a ball and then watched that motion play backward, the math would still check out. So, why does real life not behave that way? Why is every moment we live in glued so firmly to the next one in a sequence that cannot be shuffled or reversed? Good evening, curious minds. I truly hope you will enjoy today's video. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing, but only if you enjoy these calm journeys through the universe. Now, let's begin. Part of the problem is that we take time for granted. We treat it like a steady stream flowing past us. But maybe it is not the stream that moves. It is us. Imagine being frozen in a river of still moments, each one a frame of reality. What we call time passing might just be our consciousness sliding across these frames, experiencing them in order. If that sounds mind-bending, it is because time is not a thing you can hold or touch. It is not even something you can see. It is something you feel. Our entire sense of reality depends on time's arrow. You wake up, brush your teeth, spill coffee on your shirt, and go to work, all in that order. You cannot mix it up, no matter how hard you try. But beneath that ordinary routine lies an extraordinary mystery. Why should time have a preferred direction at all? Why should events unfold toward the future instead of the past? The universe could have been designed symmetrically, like a movie that plays just as well backward as forward, but it is not. The cosmic film reel only ever turns one way, and this one-wayness is not just philosophical, it is physical. Every clock that ticks, every leaf that falls, every heartbeat that keeps you alive is a declaration that the universe is moving forward. Even decay is a timestamp. When something rots, melts, or cools down, it is simply time leaving its fingerprints. You can think of it as the universe's handwriting, messy, but consistent. The ancients tried to understand this mystery long before we had physics. To them, time was divine, something gods or spirits controlled. They built sundials and calendars not to command time, but to worship its passage. And while we have since replaced mythology with mathematics, that sense of awe remains. Because even today, with all our science, time still will not explain itself. Try to imagine time stopping just for a second. Everything freezes. No sound, no motion, not even thought. You would not even notice that time had stopped, because noticing requires time. That is the eerie paradox of it. You cannot step outside time to observe it. You are trapped inside, forever moving with it, like a passenger who cannot see the train tracks. And yet, while we cannot reverse time, we can play with it. Memory lets us travel backward in our minds, revisiting old moments even though we cannot physically return to them. We store the past inside us, carrying tiny archives of what once was. It is the closest thing humans have to a time machine, a fragile biological recording that blurs, fades, and edits itself over years. Memory is proof that while the universe refuses to rewind, our minds can still peek into the rearview mirror. Then there is our obsession with clocks. Humanity has spent centuries trying to measure something that refuses to be tamed, from sundials and pendulums to atomic oscillations. We keep trying to pin time down to the smallest fraction of a second. But no matter how precise the tick, it still only moves in one direction. The hands never turn back by themselves. Clocks are like mirrors that only reflect forward. What makes time especially maddening is that it feels both infinite and fleeting. You have all the time in the world until you don't. You cannot store it, stretch it, or reroute it. You can only experience it as it passes, moment by moment, never twice the same. In that sense, time is the ultimate currency. Everyone spends it, no one earns it back, and inflation is measured in wrinkles. But the deeper question remains: why does it only go one way? Why do we age forward and not backward? Why can we remember yesterday but not tomorrow? The universe could, in theory, allow both directions, but something pins it firmly toward the future. This chapter is just the first step toward uncovering that reason. Later, we will discover how the hidden physics of entropy, probability, and cosmic history sculpt this one-way road we call time. For now, it is enough to understand that the arrow of time is not just a feature of the universe. It is the stage on which the entire story of existence unfolds. Every sunrise, every heartbeat, every galaxy drifting farther away, all of it is time's handwriting on the cosmic canvas. And while we might dream of rewinding the reel, the universe seems content to play its movie once, in one direction only. No sequels, no reruns, just an endless premiere. Every game has rules. You can't move a rook diagonally in chess. You can't touch the ball with your hands in soccer. And you definitely can't convince the universe to let you live last week again. The cosmos, as it turns out, is the strictest referee imaginable. No negotiations, no appeals, no second chances. Its first and most unbreakable rule: time flows forward, always. And that rule isn't just a suggestion. It's woven into the very fabric of the laws that govern everything from galaxies to atoms. The universe doesn't just experience time, it obeys it. Imagine the laws of physics as the universe's operating system. Every particle, planet, and person runs on the same code. That code defines what can happen, what can't, and crucially, when things happen. In this system, time is not some optional feature you can toggle on and off. It's the central clock that keeps every cosmic process in sync. Without it, motion, change, and cause itself would collapse into static nonsense. To understand why time has to move forward, we need to realize how deeply the concept of cause and effect is tied to it. Cause and effect are like cosmic dance partners. You can't have one without the other. Drop a rock, it falls. Flip a switch, the light turns on. You expect the cause to precede the effect, never the other way around. If it did, life would feel like a bad movie edit, where the explosion comes before the match is lit. The universe agrees. It insists on order. Time's direction enforces that order. Without it, everything from chemistry to consciousness would unravel into chaos. This law of one-way causality is so universal that we barely notice it. You don't sit around wondering whether breakfast will make you hungry yesterday. But in physics, that simple expectation represents a profound truth. The laws of nature, while mostly symmetrical, seem to conspire to keep causality safe. Gravity pulls objects both forward and backward in equations, but in practice, we only ever see apples fall, not leap back into trees. Somewhere deep within the machinery of reality, a rule says, events must line up forward. What's fascinating is that time's direction is not immediately obvious in the math that describes the universe. The core equations that rule motion, energy, and forces, the big players like Newton's laws, Maxwell's equations, and even Einstein's relativity, don't technically forbid time from running backward. The math works either way. It's as if the laws of physics are bilingual, fluent in both forward and backward time. But the universe clearly prefers one language. So what's enforcing that preference? Think of it like software defaults. The code might allow multiple options, but only one gets activated when you boot up the system. Somewhere in the cosmic startup sequence, the universe picked time runs forward as its default setting, and it's been running that way ever since. The reasons why are buried in deeper layers of physics. But what matters here is that every physical law we know bends around that choice. Consider motion. An object in motion will stay in motion unless acted upon by an external force. That's Newton's first law, a timeless rule, right? Not quite. The moment you add friction, heat, or any form of energy transfer, time creeps in. Friction doesn't just slow things down, it converts energy into heat, spreading it out irreversibly. Once that happens, the system cannot return to its original state without outside help. The rulebook says, you can lose order naturally, but you can't gain it back for free. That is, the physical definition of direction. Even light, the universe's ultimate speed limit, bows to this rule. Light doesn't travel backward through time. Its entire behavior depends on emission, travel, and absorption. 3 steps that always unfold in sequence. You can't shine a flashlight and expect the light to rush back into the bulb. The equations describing light's motion might not mind the reversal, but reality does. Something in the universe's rulebook enforces the script. Emit first, absorb later. But maybe the most poetic example is in decay. Take a radioactive atom. It sits there, stable for a while, and then pop, it decays. Energy and particles fly out. The timing of that event is random, but the direction isn't. You'll never see decay run in reverse. The fragments won't suddenly come back together, reassembling the original atom like a cosmic magic trick. Decay is irreversible. It's one of nature's signatures that says, this event happened, and there's no undo button. Now, it's tempting to think of time as some mysterious current flowing independently, but in reality, it's not something separate from the universe's rules. It is one of them. Time is built into space-time itself, the 4-dimensional stage where everything exists. Einstein's relativity showed us that time and space are inseparable. They bend, stretch, and warp together. But even within that flexibility, time refuses to reverse direction. Gravity might slow it, motion might stretch it, but neither can flip it. That steadfastness hints that the forward flow of time isn't just a property of experience. It's a physical law that the universe enforces without exception. In that sense, time is not just another dimension. It's the backbone of the rule book. You can walk left or right, up or down, but you can't walk before. The universe allows 3 dimensions of freedom and 1 direction of surrender. You can move anywhere in space, but in time, you're a one-way traveler. So, if the universe truly has a rule book, time's direction is not written in pencil. It's carved into the cover. It's what keeps dominoes falling the right way, galaxies spinning the right way, and life itself unfolding the right way. Without this rule, nothing could evolve, grow, or even remember. Everything would simply exist as a static blur of all possible moments, frozen forever. But because time has a direction, the universe can tell stories. Stories of stars being born, of worlds cooling, of people learning, loving, and leaving traces behind. The no rewinds rule might sound harsh, but it's also the reason anything happens at all. The cosmos is not cruel, it's consistent. And consistency, in physics and in life, is what makes everything else possible. Imagine standing in your kitchen holding an egg, a fragile little capsule of order, everything neatly arranged, smooth shell, liquid yolk, perfectly contained. Now, drop it. It shatters, splattering across the floor in a Picasso of regret. You watch the goo spread and think, well, that's irreversible. And that feeling? That's entropy in action. The egg doesn't reassemble, the shell doesn't magically glue itself back together, and your kitchen doesn't volunteer to clean itself. The laws of physics are fine with destruction, but they frown upon tidy miracles. Entropy is the universe's built-in tendency toward disorder, the great cosmic shrug that says, things fall apart. It is not just about chaos or mess, it is about probability. There are far more ways for things to be disordered than to be neatly arranged. Think about your sock drawer. There's exactly one way for every pair to be folded, sorted, and color-coded, but an infinite number of ways for them to be mismatched, tangled, and mysteriously missing one partner. Nature plays by the same odds. Order is rare, disorder is easy, and the universe, being efficient, goes where the odds are better. This preference for disorder is written into the second law of thermodynamics, which states in human terms that energy naturally spreads out unless you stop it. It's the law that makes ice melt, coffee cool, and stars eventually burn out. Entropy measures how spread out energy is, how evenly things are mixed. The more uniform, the higher the entropy. When you mix cream into coffee, the swirling chaos that follows is entropy increasing. It's not evil, it's inevitable. Now here's where things get weird. Entropy might be the real reason time moves forward. The flow of time, the feeling that after follows before, might not be a fundamental rule at all. It might be a side effect of everything falling apart. In physics, there's no separate law that says time must move in one direction. But there is a law that says entropy must increase, and that gives us an arrow to follow. The past is the direction where things were more ordered. The future is where they're more mixed up. Time's arrow is really just entropy's arrow wearing a watch. To get a sense of why entropy defines time's direction, picture a deck of cards. Start with it perfectly sorted. Aces, then twos, then threes, all in order. Shuffle it once, twice, 50 times. The more you shuffle, the more mixed up it gets. You can shuffle for eternity, but you'll almost never get that perfect order again. Not because it's impossible, just because it's improbable. The universe behaves the same way. Once it's shuffled into disorder, the chance of it reorganizing spontaneously is vanishingly small. That statistical tilt gives time its forward push. This also explains why we remember the past and not the future. Memory, after all, is an ordered arrangement of information. Neurons storing patterns. The past was more ordered, more defined. The future hasn't happened yet because it's part of the unfolding chaos that hasn't settled into form. Our brains evolved to record the low entropy configurations of events as they occur. You don't remember tomorrow for the same reason your spilled egg doesn't jump off the floor. It hasn't organized yet. Entropy shows up everywhere once you start looking for it. Open your refrigerator, and it's there in the form of heat exchange. Step outside, and it's in the way clouds disperse and leaves decay. Even in your body, Entropy is the silent engine running every moment. Your metabolism is a fight against it, a biochemical war to maintain order by burning energy. Every heartbeat, every breath, every calorie you consume is your body paying the price to stay structured in a universe that loves to unravel things. But before you start thinking entropy is the villain of the story, let's give it some credit. Without it, nothing would happen. A perfectly ordered universe would be frozen. No change, no growth, no movement. Entropy creates the contrast that allows things to evolve. Stars ignite because hydrogen collapses inward, increasing entropy in the process. Life itself thrives on controlled disorder. You, sitting there thinking about entropy, are a local pocket of order fueled by the universe's overall slide into chaos. You are, in a poetic sense, organized decay with opinions. The brilliance of entropy lies in its simplicity. It doesn't need to want anything, it just counts possibilities. If there are 1 billion ways for energy to scatter, and only one way for it to stay clumped together, odds are it'll scatter. It's the same logic behind why your room doesn't spontaneously clean itself overnight. The molecules of dust and clothes could, in theory, arrange themselves neatly while you sleep. But the chances are so absurdly tiny that you'd sooner win every lottery in the galaxy at once. Scientists often say entropy measures disorder, but that word undersells it. Entropy measures information, the number of possible microscopic arrangements that correspond to what we see macroscopically. When you break an egg, you haven't destroyed information. You've just scrambled it beyond recognition. The system's details still exist, but they're too tangled to reconstruct. It's like deleting a file. The bits are still somewhere on the drive, but good luck finding them. What makes entropy so fascinating is that it connects the tangible with the philosophical. It tells us that the universe's story is not one of decay, but of transformation. Every process, from the birth of galaxies to the melting of an ice cube, is part of the grand redistribution of energy and order. Entropy is the universe mixing its deck, an eternal shuffle that keeps everything dynamic. So, when we say time goes forward, what we really mean is entropy increases. Broken eggs, melting ice, aging faces, they're all symptoms of the same deep law. The universe keeps rearranging itself toward greater disorder because that's the most likely outcome. And while that sounds bleak, it's actually the reason anything ever happens. Without entropy's push, we'd live in a static, motionless void, a universe that never changes, never grows, never even begins. In other words, entropy isn't just the culprit behind time's arrow. It's the reason the arrow exists at all. It's why stars burn, why memories fade, and why your morning toast will never untoast itself, no matter how hard you stare at it. Time doesn't flow because clocks tick. Clocks tick because time is flowing, and entropy is the hand winding them forward. If the universe had a personality, entropy would be its lazy side. It's that cosmic teenager who starts off with a tidy room but somehow ends up living in a laundry avalanche, surrounded by the fossilized remains of snacks. The universe began neat and compact. Energy and matter tucked together neatly in a low entropy bundle. But it has been getting progressively messier ever since. And the direction of that messiness, that slow but unstoppable drift toward chaos, is what we call the future. When physicists talk about entropy loving the future, they mean something quite specific. The future isn't just a place we haven't reached yet. It's a direction in which disorder naturally grows. Time and entropy are not two separate rivers. They're the same current, seen from different angles. Wherever entropy increases, we point and say, that's forward. The future, therefore, is the direction that entropy chooses to flow. To see this in action, imagine releasing a drop of ink into a glass of water. At first, it forms a perfect dark sphere. But within seconds, it starts to swirl, stretch, and diffuse until the whole glass becomes uniformly grey. You could film that process and play it forward or backward. But only one version would look natural. Watching ink unmix, gathering itself into a perfect drop, would feel wrong because it would violate entropy's preference for spreading out. In that sense, the future is simply the version of events where things continue to disperse, smooth out, and get more random. But why does entropy always head that way? Why doesn't it sometimes take a day off and run backward? The answer lies in probability. There are infinitely more ways for a system to be disordered than for it to be perfectly organized. Consider a deck of cards again. There's only one perfect order, but countless ways to shuffle it. The universe doesn't want to be messy. It just can't resist the math. As time passes, the odds overwhelmingly favor the spread of energy, the mixing of particles, and the loss of clear structure. It's not that the universe is falling apart. It's just exploring the most statistically likely configurations. This tendency gives rise to one of the most elegant illusions in physics, that time moves. In reality, what we experience as time passing may simply be the unfolding of entropy, each moment containing slightly more disorder than the one before. The ticking of clocks, the aging of stars, the decay of atoms, all are markers of entropy increasing. The future is where the deck gets more shuffled, and we can never go back to a previous hand. In your daily life, you experience this cosmic preference constantly, even if you don't notice. You can scramble an egg, but not unscramble it. You can crumple paper, but not uncrumple it perfectly. You can mix cream into coffee, but you'll never see the cream leap out and reform. These are all everyday demonstrations of entropy's favorite direction: forward. The future is literally the space where everything has been mixed a little more than before. Even memory, perception, and consciousness bow to this arrow. The reason you can remember your past, but not your future, is that the past is a record of lower entropy. a state where information was still structured enough to be stored. The future, by contrast, is a fog of increasing disorder, where structure has not yet emerged. Your brain, as a physical system, can only record changes that move from order to disorder, because that's how energy flows through it. In a high-entropy universe, memory is the footprint that order leaves behind as it collapses into chaos. To understand why entropy loves the future, think of the universe as a grand mixing machine. In the beginning, everything was tightly packed, smooth and uniform. Over billions of years, gravity pulled matter into stars and galaxies. Heat spread through radiation, and energy dispersed across vast distances. This expansion is not just spatial, it's entropic. The universe is stretching its own potential for disorder. Each new star that burns, each planet that cools, each black hole that swallows matter, adds a little more to the grand tally of entropy. The future, then, is simply where there's more room for the mess to grow. This has an oddly comforting implication. The future is built not on precision, but on possibility. It's not a single, predetermined path, but a field of increasing probability. Entropy ensures that, as time moves forward, systems become less predictable, not because the universe is chaotic in the emotional sense, but because there are so many more ways for things to unfold. The further you move into the future, the more potential arrangements there are. That's why surprises, creativity, and even life itself thrive there. Entropy opens the door to complexity by making the universe flexible enough to explore new combinations. Ironically, while entropy drives things toward disorder, it also makes local order possible. A hurricane, for instance, looks like chaos, but it's actually a highly organized structure that arises from the larger scale disorder of heat flowing from warm oceans into cool air. Life operates on the same principle: tiny islands of order sustained by the surrounding sea of chaos. Your body maintains structure only by burning energy and exporting entropy to the environment. You're like a candle, flame on the outside, disorder in the wake. Without the overall increase of entropy, there'd be no reason for energy to flow. And without flow, nothing would live or evolve. So when we say entropy loves the future, it's not poetic fluff, it's literal physics. The future is the natural endpoint of entropy's march. Each moment that passes is a little less structured, a little more spread out, a little further from the tight, low entropy beginnings of the cosmos. The arrow of time, then, is just the record of entropy's expanding domain, a kind of cosmic graffiti spelling out more randomness ahead. The beauty of it is that this march toward disorder doesn't erase meaning, it creates it. Every pattern, every spark of life, every fleeting moment of order is a rebellion against entropy's drift, a temporary sculpture carved from the flow of time itself. The universe may not clean its room, but it sure knows how to make art from the mess. And that's the heart of it. The future is simply the place where entropy keeps playing. where new patterns emerge even as old ones dissolve. It's not a destination, it's a direction. And no matter how neatly we try to fold reality, the cosmos will always leave its socks on the floor. If you've ever tried to keep a room clean for more than 2 consecutive days, you already understand entropy. No matter how often you fold, dust, and rearrange, the universe seems to be quietly conspiring against you. It's not personal, it's probability. The universe isn't trying to make a mess. It's just really, really likely that it will end up with one. Time's relentless march forward isn't a magical commandment written in cosmic ink. It's a statistical preference. The future is simply the direction where the odds of messiness win by a landslide. To grasp this, you have to think like a gambler rather than a philosopher. Imagine the universe as a giant casino, where every roll of the dice represents the arrangement of matter and energy. There are far more dice rolls that produce messy results than ones that land on a perfectly ordered combination. Entropy doesn't force disorder. It just says that disorder is the most probable outcome when you let the dice keep rolling. The forward flow of time is what happens when the universe keeps winning the same bet. That there are more ways for things to fall apart than to stay arranged. This is what makes entropy such a subtle trickster. It masquerades as a law of inevitability, when in reality, it's a matter of statistics. The second law of thermodynamics, the one that says entropy always increases, isn't about a cosmic rule that says things must get worse. It's about what's most likely to happen in a system with countless particles all bouncing around, colliding, and rearranging. On the atomic level, the universe doesn't prefer disorder. It just plays the odds, and the odds are spectacularly one-sided. To make that concrete, picture a simple example. A box divided into 2 halves with all the air molecules initially sitting neatly on one side. That's a state of low entropy, orderly and improbable. Remove the divider and the molecules start bouncing around, quickly spreading into both halves of the box. Why? Because there are trillions upon trillions more arrangements where the molecules are evenly spread than where they're all huddled in one corner. The air doesn't want to expand, it's just overwhelmingly likely to do so. If you left it alone long enough, the molecules could randomly gather back into one half again. But the probability of that happening is so absurdly tiny that you'd need to wait longer than the lifetime of the universe to see it. And that's the heart of it. The universe doesn't forbid the past. It just makes it statistically extinct. The reason we never see broken cups spontaneously reassemble or heat flow from cold to hot is because those events are so improbable that for all practical purposes, they might as well be impossible. Entropy gives time direction, not through prohibition, but through probability. The future isn't where rules change, it's where the math points. Even the notion of irreversibility is really a shorthand for statistical bias. The microscopic laws that govern particles, like Newton's equations or Schrödinger's wave function, are perfectly reversible. If you reversed every motion of every atom in a glass of spilled water, it would unspill flawlessly. Physics wouldn't object. The problem is that to do this, you'd have to know and control the position and velocity of every single molecule with impossible precision. One tiny mistake, a single atom off course, and the process derails into chaos. Reversing time isn't impossible because the laws forbid it. It's impossible because the odds are stacked to cosmic extremes. This statistical trick also explains why time feels so consistent. The future seems inevitable not because of divine decree, but because we are embedded in a system where the most probable outcome happens so consistently that we call it normal. You don't notice entropy increasing in your everyday life because the universe doesn't need to roll the dice many times before landing on messy. That's the winning number nearly every time. It also means that the arrow of time is, in a sense, emergent, a byproduct of the overwhelming imbalance between order and disorder in probability space. Time moves forward because that's the direction where uncertainty expands. Think of it like shuffling a deck of cards. Each shuffle multiplies the number of possible orders, even though the underlying rules of shuffling haven't changed. The deck isn't forbidden from becoming perfectly sorted again. It's just astronomically unlikely. Time's direction, therefore, isn't enforced by any cosmic cop. It's simply what happens when you keep shuffling reality. This also hints at something profound about the beginning of the universe. If time's arrow points toward higher entropy, that means it must have started from a remarkably low entropy state, a kind of cosmic clean slate. The early universe was astonishingly smooth and ordered, with energy distributed evenly across space. In statistical terms, it was an incredibly rare hand of cards. As it evolved, gravity, heat, and motion took that neat deck and began to shuffle it. The reason time flows at all is because we started with such an unlikely arrangement in the first place. If the universe had begun in a completely random, high entropy state, there wouldn't even be a direction to time, just a stagnant blur of sameness. But the beauty of probability is that it doesn't just create decay, it creates variety. As entropy increases, systems explore new configurations, new possibilities. That's why stars form, burn, and die. It's why life can exist in the first place. Entropy doesn't destroy structure. It allows new structures to emerge temporarily before dissolving again into the great statistical sea. You could say the universe is a gambler who loses slowly but enjoys every game. So, when we say the universe is a lazy housekeeper, we mean it statistically. It's not that the universe refuses to clean. It's that cleaning takes incredible precision, while messes happen effortlessly. The cosmic odds are tilted toward clutter. And yet, out of that clutter, extraordinary things happen. Storms, galaxies, civilizations. The universe doesn't micromanage, it lets probability sculpt beauty out of chaos. In the end, time's arrow is just the shadow cast by probability. The future is where the messy outcomes live. And since there are infinitely more of those than tidy ones, that's where we all end up heading. The universe doesn't need to force us forward, it just lets the numbers play out. And statistically speaking, the odds are never in favor of going back to fold the laundry and leaving traces behind. The no rewinds rule might sound harsh, but it's also the reason anything happens at all. The cosmos is not cruel, it's consistent. And consistency, in physics and in life, is what makes everything else possible. If time moves forward because entropy increases, there's an obvious but rarely asked question lurking in the background. Why was the universe's entropy so low to begin with? It's like watching someone push a boulder down a hill and realizing that before it rolled, they had to carry it all the way up there first. The forward flow of time, the grand march toward chaos, depends entirely on a strange fact about the beginning of everything. At the moment of the Big Bang, the cosmos was astonishingly neat. That's the real mystery of time's arrow. If entropy gives time its direction, then the reason time has a direction at all must lie in the way the universe started. The Big Bang wasn't just the beginning of space, matter, and energy. It was also the birth of order itself. Everything was compact, smooth, and almost perfectly uniform. In other words, the universe began as a tidy desk before someone spilled galaxies all over it. Let's pause for a moment to appreciate how weird that is. The early universe was unimaginably hot, dense, and filled with energy. It might seem like that would be a chaotic mess, but it wasn't. It was smooth, so smooth in fact, that if you measured the density of matter across vast regions, you'd find almost no variation at all. That uniformity is what physicists mean when they say the universe started in a low entropy state. Despite all that energy, it was an orderly kind of energy, neatly balanced, evenly distributed, like an oven preheated to perfection before baking begins. So why did it start that way? Why didn't the universe begin in the disordered, high entropy state it seems destined to reach in the future? That question has baffled physicists for decades because it digs at the foundations of both cosmology and time itself. If entropy defines the future, then the early universe's low entropy defines the past. But who or what set the initial conditions? One idea is that the Big Bang wasn't random at all, but rather a result of incredibly precise physical conditions, like the universe booting up in its lowest energy configuration. The laws of physics might have demanded that smooth beginning, just as a computer must start from a clean state before it can begin computing. In this view, low entropy was the cosmic default, and time's flow is simply the process of the universe running through its instructions. Another idea, more speculative but tantalizing, is that what we call the Big Bang might not have been the beginning of everything, just the start of our version of time. In that case, the smoothness of the early universe could be the result of something that happened before time, some kind of pre-cosmic condition or bounce from a previous universe. If that's true, then the arrow of time we experience might just be one half of a larger loop, with entropy increasing in both directions, away from a central moment of perfect order. In other words, what we call the beginning might actually be the middle. But even without speculating about cosmic cycles, the low entropy of the Big Bang remains one of the strangest clues in modern physics. The simplest explanation might be gravity itself. Unlike other forces, gravity behaves in a way that flips our intuition about disorder. In most systems, spreading things out increases entropy. But gravity likes clumping. A uniform distribution of matter, like the early universe, is actually a very low entropy configuration, because gravity hasn't yet started its messy work of forming stars, black holes, and galaxies. Once gravity kicks in, matter collapses into dense structures, releasing energy and spreading disorder throughout the cosmos. So the Big Bang might have looked like a firestorm, but gravitationally speaking, it was pristine, a blank canvas waiting to be splattered. It's as if the universe began at the top of a mountain, perfectly balanced, and time's arrow is the tumble downward. Every second that passes, gravity sculpts more structure, burns more fuel, and spreads more heat. Entropy grows, not because the universe began chaotic, but because it began poised in an extraordinarily special state that allowed it to become chaotic over time. That delicate beginning gave the universe something to do. Here's the twist. That low entropy starting point was absurdly improbable. The late physicist Roger Penrose once calculated that the odds of the universe beginning in such an ordered configuration were 1 in 10 to the power of 10 to the power of 123. A number so massive that writing it down would take more ink than exists in the observable universe. And yet, that's the state we got. It's as though the cosmic dice rolled the most unlikely combination imaginable, and that perfect roll is what gave us time. Why it happened remains one of the great unsolved puzzles. Some physicists think the early universe's inflationary expansion, an ultra-rapid swelling of space just after the Big Bang, might have reset conditions, smoothing everything out like a cosmic ironing board, before entropy had a chance to spike. Others argue that the universe's laws themselves might inherently favor simplicity at the start. Still others whisper that maybe initial conditions are an illusion, that time's direction only emerges later. And asking why it started low is like asking what's north of the North Pole. No matter which theory wins, one fact stands firm. Our sense of time depends on that improbable beginning. Every clock tick, every heartbeat, every supernova is the universe sliding downhill from that mountain of order toward the valleys of disorder. Time is not just a story of things changing. It's the memory of a beginning that was almost impossibly neat. So when you look up at the night sky, glittering with stars born from gravitational collapse, you're seeing entropy's masterpiece in progress. You're seeing the universe mid-marathon, running downhill from its remarkably smooth starting line. The fact that we even exist in this fleeting, structured moment between order and oblivion is a testament to how special that beginning was. The cosmos didn't just start the race, it started it on the highest peak imaginable, with a view of eternity ahead. And every second that passes, every atom that cools, is just us rolling farther down that mountain, carried by the secret of the Big Bang, a single act of impossible order that set the entire river of time flowing. If Isaac Newton imagined time as a steady, universal drumbeat, tick, 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 the same everywhere, Albert Einstein came along and kicked the drum down a hill. In Newton's world, time flowed evenly for everyone, like a perfectly synchronized cosmic clock. But Einstein shattered that idea in 1905 with his theory of relativity, and again in 1915 when he wove gravity into the mix. His revelation was both elegant and unsettling. Time doesn't move the same for everyone. It bends, stretches, slows, and sometimes practically stalls, depending on where you are and how fast you're moving. The universe, it turns out, doesn't have one clock. It has 7 trillion, and they rarely agree. To grasp how radical that was, imagine 2 friends. Let's call them Maya and Leo. Maya stays home on Earth. Leo blasts off in a spaceship at nearly the speed of light, zipping around the galaxy before returning. When he lands, he's barely aged, while Maya has lived decades. That's not science fiction. It's relativity in action. Time literally slowed down for Leo because of his motion. His clock ticked fewer times than Maya's. From her point of view, he's a time traveler who skipped through the years simply by moving fast enough. This isn't a glitch in the math, it's the math itself. According to Einstein's special relativity, the faster you move through space, the slower you move through time. Space and time aren't separate entities. They're 2 sides of the same 4-dimensional coin called spacetime. If you spend more of your motion budget on space, you have less left for time. You can think of it like a cosmic speed limit for experience. Move fast enough, and time politely steps aside to let you pass. But that's just the appetizer. Einstein's general theory of relativity, published 10 years later, took the idea further and introduced gravity into the mix. And that's when time truly got weird. Gravity, he realized, isn't some invisible force pulling objects together, as Newton thought. It's the warping of space-time itself. Massive objects like planets, stars, and black holes bend the fabric of reality around them, and time flows differently depending on how deep you are in that gravitational well. The closer you get to something massive, the slower time runs. It's not an abstract effect either. We've measured it. The clocks on GPS satellites orbiting Earth tick slightly faster than clocks on the ground because they're farther from the planet's gravity. If engineers didn't correct for that difference, your navigation app would send you driving confidently into a lake. Gravity literally pulls on time, stretching it out like taffy. Einstein's universe isn't a flat stage where events play out. It's a flexible, dynamic sheet that curves under weight. Time, in that view, isn't just passing, it's flowing unevenly. The implications are as bizarre as they are beautiful. On a small scale, time dilation, this stretching and squeezing of time, is almost imperceptible. But take it to extremes, and you get something cosmic. Near a black hole, for instance, time slows to a crawl. From far away, you'd see someone falling toward the event horizon, freeze in place, their clock ticking slower and slower until it seems to stop entirely. From their point of view, though, they'd plunge through without noticing anything unusual. Time is personal. What happens to one observer may look impossibly strange to another. This relativity of time demolishes the idea of a universal now. There is no single moment that everyone in the universe shares. What is happening right now on a distant galaxy depends entirely on how you're moving and where you are. Two observers could disagree about the order of events, who did what first, and both could be right. Time is not a river flowing past us at a steady rate. It's a landscape, and we each take our own path across it. Einstein once described this new vision of time as the stubborn illusion of absolute simultaneity. In his universe, time is woven inseparably with space, and together they create a fabric that can twist, stretch, and ripple. Even light, the fastest thing there is, must obey the curves of this fabric. That's why starlight bends around the sun, and why galaxies act as gravitational lenses, warping the light of objects behind them. It's also why gravity feels stronger in some places than others. It's not a force pulling down. It's space-time telling you which way straight happens to be. And here's where it gets philosophical. If time can bend and slow, then maybe it doesn't flow at all. Maybe all moments, past, present, and future, exist simultaneously within the fabric of space-time. Physicists sometimes call this the block universe model, where time isn't a moving river, but a frozen landscape. You and I, and every event that ever happened or will happen, exist as part of that four-dimensional block. What we call the passage of time is simply our consciousness sliding along our own timeline, like a flashlight scanning across a mural. The light moves, but the painting doesn't. That's an unsettling thought. It suggests that the future might already exist, waiting patiently, and that the past hasn't vanished. It's just somewhere else in the space-time tapestry. Einstein himself was deeply comfortable with that idea. When his close friend Michel Besso died, Einstein wrote to his family, "For us convinced physicists, the distinction between past, present, and future is only a stubbornly persistent illusion." Comforting words from a man who had quite literally bent time to his will. Yet, despite its elegance, relativity doesn't answer why time feels like it moves forward. It only tells us that it moves differently depending on where you stand. The arrow of time, the sense of before and after, comes from entropy, not relativity. But Einstein's theories revealed something even deeper. That time's flow, isn't universal, it's local. Each of us carries our own pocket of time, stretching and contracting with motion and mass. It's humbling to realize that when you look at the stars, their clocks are ticking at different speeds than yours. Somewhere, billions of light years away, an entire civilization might be living through a moment that to us won't exist for eons. The cosmos isn't synchronized. It's jazz, fluid, flexible, and beautifully out of rhythm. So the next time you're annoyed about daylight saving time, take comfort in knowing that's nothing compared to the real cosmic confusion. Time zones might make you late for a meeting, but relativity means there's no such thing as late in the first place. Only local versions of now stitched together on the stretchy, shimmering fabric of space-time. If you've ever wished for a do-over, a chance to unsay that one text, to stop yourself from eating that week-old sushi, or to buy stock in a certain online bookstore back in 1997, then you've wished for time travel. It's one of humanity's favorite daydreams, sitting comfortably between flying and being invisible. Science fiction made it glamorous. Einstein made it almost plausible. And yet, despite all the equations that wink and whisper, hey, maybe it's possible, reality itself seems to cross its arms and say, don't even think about it. Let's start with the good news. The laws of physics don't explicitly forbid time travel. In fact, Einstein's general theory of relativity, our best description of space, time, and gravity, has solutions that allow for paths through space-time that loop back on themselves. These are called closed time-like curves, which is a fancy way of saying routes where you can travel forward in time and end up in your own past. In the math, it works. On paper, you can draw a line through space-time that curls back like a cosmic pretzel, connecting tomorrow to yesterday. One of the first scientists to notice this was Kurt Gödel, a friend of Einstein's, who in 1949 found a strange solution to Einstein's equations. His hypothetical universe rotated as a whole, and in that spinning cosmos, time could, in theory, loop around. You could hop in a spaceship, take the right path, and return to the moment you left. It was mathematically sound, but completely absurd in practice. A universe like that would require the entire cosmos to be twisting, like a giant intergalactic tornado. Still, the fact that relativity allowed such a solution made physicists uneasy. Einstein himself wasn't thrilled. He'd opened a mathematical door that seemed to lead straight into a science fiction novel. Since then, theorists have discovered other potential time travel solutions hiding in Einstein's equations. The most famous are wormholes, those hypothetical tunnels that connect distant points in space-time. If one mouth of a wormhole experiences time differently than the other, say by being moved near a strong gravitational field or accelerated to near light speed, the two ends could become misaligned in time. Step through one mouth and you might pop out the other side in the past. Congratulations, You've built yourself a cosmic shortcut and a paradox generator. But here's where the bad news begins. Wormholes, while beautiful in theory, are infuriating in practice. First, no one has ever found one. Second, even if they exist, keeping one open would require a substance called exotic matter, material with negative energy density, the kind of stuff that doesn't appear to exist in the real universe. Without that, a wormhole would collapse faster than you can say chronological catastrophe. It's like trying to build a tunnel out of soap bubbles. Great for a thought experiment, not so great for engineering. And then there's the problem of paradoxes. Time travel isn't just a question of physics. It's a test of logic. The classic example is the grandfather paradox. If you go back in time and accidentally prevent your grandfather from meeting your grandmother, then you wouldn't be born to go back in time in the first place. The entire sequence folds in on itself like a Mobius strip of confusion. The universe seems to abhor contradictions as much as it abhors low entropy. So even if you could travel to the past, something, perhaps probability itself, might stop you from changing anything meaningful. Physicist Igor Novikov tried to make sense of this by proposing the self-consistency principle. It states that if time loops exist, events within them must always be consistent. You can go back and interact with the past, but whatever you do becomes part of history, not a change to it. You can't prevent your grandfather's date. You might just end up being the waiter who served them their drinks. The timeline edits itself to maintain coherence. Reality, in this view, is a strict editor. You can write within the margins, but the story's ending is non-negotiable. Even so, time loops pose practical nightmares. They'd require energies beyond anything we can produce and control. To bend space-time enough to loop it back on itself, you'd need the mass of a star compressed into something smaller than an atom. Black holes come close, they do warp time dramatically, but they don't offer safe passage. Their singularities are one-way trips, not scenic routes through history. And let's not forget quantum mechanics, that ever-smirking trickster of modern physics. When you try to combine relativity with quantum rules, time travel becomes even more unstable. Quantum fluctuations could build up in a time loop, amplifying endlessly until the whole thing collapses. It's as if the universe enforces a no paradox policy by making time machines self-destruct under their own quantum tantrums. Stephen Hawking famously called this the chronology protection conjecture, the idea that the laws of physics conspire to prevent time travel altogether. The universe, he joked, seems to dislike time machines, and it's taking steps to make sure none are ever built. Still, the temptation to imagine persists. Physicists have toyed with wild concepts, rotating black holes called Kerr singularities, cosmic strings, infinitely long filaments of energy that could, in theory, twist space-time into loops, and even quantum time teleportation. Yet every idea hits the same wall. Either it demands infinite energy, breaks causality, or requires substances that might as well belong to a wizard's ingredients list. The math smiles, but the universe frowns. What's fascinating, though, is that relativity does give us a kind of time travel. It just only works one way. Every time you move faster, climb a mountain, or orbit Earth, your clock runs a little differently than everyone else's. Astronauts on the International Space Station have technically traveled a few milliseconds into the future relative to us. It's not much, but it's real. You don't need a DeLorean, just a really good clock and some patience. So, for all our dreaming, the verdict stands. Time travel is theoretically possible, but practically ridiculous. The universe leaves the door cracked open, only to shove a "Do not enter" sign in our faces. Still, maybe that's a mercy. A world where anyone could rewrite the past would be chaos. The arrow of time may be strict, but it keeps the story coherent. And besides, who needs a time machine when the universe is already taking us, moment by moment, into the future, for free and without paradox insurance? If relativity treats time like a flexible fabric, then quantum mechanics takes that fabric, crumples it into a ball, tosses it in the air, and asks, "So, which way is forward again?" At the subatomic level, where particles blink in and out of existence, faster than you can say uncertainty principle, time stops behaving like a polite, orderly procession. Instead, it becomes something fuzzy, inconsistent, and occasionally mischievous. In the quantum world, the tidy sequence of cause and effect starts to unravel. Particles don't just exist, they exist in possibilities. They can be here and there, doing this and that, all at once, until someone, or something, measures them. Then, as if caught in the act, they suddenly pick a side. That alone is weird enough. But here's where things get truly mind-bending. Some of these quantum effects seem to play with time itself. Let's start with the basics. Quantum mechanics doesn't treat time the way relativity does. In Einstein's equations, time and space are intertwined. In quantum mechanics, time is more of a background character. It's the stage upon which probabilities play out, not a player itself. But experiments have hinted that maybe, just maybe, time gets a few unscripted lines of its own. Take the delayed choice experiment, a twist on the classic double-slit experiment that has haunted physics classrooms for decades. In the original version, you fire particles, say photons, through two slits and see where they land on a screen. If you don't look to see which slit they went through, the photons behave like waves, interfering with themselves and creating a pattern. But if you do look, if you set up a detector to catch them in the act, they suddenly behave like particles, choosing one slit or the other. The act of observation changes the outcome. That's already strange enough, but physicists decided to push it further. In the delayed choice version, they waited until after the photon had passed through the slits to decide whether or not to measure it. Logically, that should be too late. The photon's decision should already be made. And yet, the results showed that the later measurement somehow determined what the photon had done earlier. It's as if the particle retroactively changed its past behavior based on a future event. The universe, apparently, is fine with editing its own timeline, at least on the subatomic level. Another quantum curveball comes from a phenomenon called quantum entanglement. When two particles become entangled, their properties become linked in such a way that measuring one instantly determines the state of the other, no matter how far apart they are. Einstein famously called this spooky action at a distance, because it seemed to defy the cosmic speed limit of light. But what's even spookier is that the correlation between the particles doesn't seem to care about time either. In some interpretations, it's as if the measurement on one particle doesn't just influence the other across space. It also reaches backward in time to make the outcomes line up. Cause and effect start to look less like a chain and more like a conversation. There's even experimental evidence that, under certain conditions, quantum systems can experience a kind of time reversal. In 2019, scientists used a quantum computer to perform a small-scale simulation of reversing time for a few quantum bits. The qubits were nudged into disorder, then manipulated in such a way that they seemed to spontaneously return to their earlier state. It wasn't time travel in any meaningful sense. No one's breakfast reappeared uneaten, but it demonstrated that, statistically, time's arrow can wobble on the smallest scales. So what's really going on here? Is time fundamentally reversible in the quantum realm? Not exactly. Most physicists believe these strange effects don't violate causality. They just stretch it to its limits. The laws of quantum mechanics themselves are time-symmetric, meaning they don't care whether you run them forward or backward. A particle's equations work both ways. Even if our macroscopic world clearly prefers one direction. The difference arises when those countless tiny quantum events add up to the large, messy, entropic systems we live in. The fuzziness of a single atom averages out, and the arrow of time reasserts itself. Still, the quantum world forces us to confront an uncomfortable idea. Maybe time isn't something that flows, but something that emerges. Some physicists now suspect that time, like temperature or pressure, is not a fundamental feature of reality, but a statistical illusion, a byproduct of the way we interact with the quantum fields underneath. In that picture, time doesn't exist at the most basic level. It only shows up when enough particles get together to make it meaningful. In short, the universe doesn't keep time. We do. The quantum perspective also opens the door to interpretations that blur the line between past and future entirely. In the two-state vector formalism, for example, a quantum event isn't just influenced by its past conditions, but also by its future ones. a particle's behavior depends on what lies ahead, as well as what came before. It's as if reality negotiates between what has happened and what will happen to decide what is happening. If that sounds dizzying, well, welcome to quantum physics, the only branch of science where the future occasionally sends its RSVP before the party starts. For us, these effects are invisible. You can't use quantum tricks to uneat a sandwich or to undo that text you sent at 2 a.m. The quantum rules only apply in the delicate, microscopic realm, where reality is still undecided. The moment you scale up to something as big as, say, a brain, the quantum blur collapses under the weight of decoherence. Basically, the noise of the macroscopic world, forcing all those quantum possibilities into one solid outcome. That's why electrons can flirt with the past, but humans can't. And yet, it's hard not to be enchanted by the idea that deep down, the universe doesn't play by our linear rules. Beneath the ticking of clocks and the decay of stars, there's a hidden layer of reality where cause and effect mingle freely, where time might hesitate, glance backward, and then continue on. It's not time travel, not even close, but it's a reminder that the arrow of time, so firm and commanding on our scale, may be less a law of nature and more a cosmic habit. At the quantum level, the universe whispers, forward, backward, it's all the same to me. And then, as soon as you listen too closely, it changes the subject. If you ever needed proof that time only moves forward, just try remembering tomorrow. You can't. Your brain is a one-way recording device. It only works from past to present. You can recall your first day of school, the smell of a childhood kitchen, or that one time you said something so awkward it wakes you up at 3 a.m., but you can't remember what you'll have for lunch next Thursday. It's not that the brain doesn't want to, it's that physics won't let it. Memory is our biological bookmark in the flow of time, and its one-way nature gives away something profound: the universe's bias toward the future. We tend to think of memory as purely psychological, a trick of neurons and chemistry, but it's also a thermodynamic phenomenon. Like melting ice or burnt toast, it's part of the same irreversible process that drives the cosmos. Your memories are tiny pockets of organized information in a universe that otherwise prefers chaos. In fact, your brain is, quite literally, an entropy tracking machine, writing down the trail of disorder as it unfolds. To see why memory points forward, let's start with the basic mechanics. Every time you form a memory, your brain changes physically. Neurons strengthen or weaken their connections, molecules shift, proteins fold, and chemical gradients rearrange. This process takes energy, lots of it. Your brain is only about 2% of your body weight, but burns roughly 20% of your daily calories. Why? Because remembering things is a thermodynamic workout. The act of encoding and storing information increases entropy elsewhere in your body. The brain may create order inside itself, But it pays for that order by generating heat, by spreading energy out into the environment. That's the thermodynamic arrow of time at work. To make something more organized, like a memory, the surrounding system must become more disordered. It's the same rule that governs stars forming in space or eggs frying on a stove. You can't get a neat outcome without creating a bigger mess somewhere else. So every memory you make is another small confirmation that time is moving forward. It's nature's way of saying, this happened, and there's no undoing it. The fascinating part is how deeply our perception of time depends on this biological limitation. You don't experience the passage of time directly. You experience change, and your memories are the record of those changes. Without them, you'd be trapped in an endless now, unable to distinguish cause from effect. In that sense, memory doesn't just record time, it creates it. The continuity of your consciousness, the feeling of moving through moments, is a story your brain constructs out of stored information. If you doubt that, consider what happens when memory falters. In severe amnesia, people lose their ability to recall the past, but they also lose the sense of an unfolding future. Their perception of time collapses into a flicker of the present. The arrow of time for them becomes fractured. It's as if the mind's grip on temporal direction weakens when memory fails, showing just how tightly human identity and the flow of time are intertwined. Now, if memory is tied to entropy, it makes sense that we can't remember the future. The future hasn't happened yet. It's still a low information state waiting to unfold. The past, by contrast, is high information, full of recorded events, traces, and consequences. Entropy ensures that information about what has happened gets imprinted in physical systems. Footprints in sand, fossilized bones, neural pathways, and heat radiation from ancient stars. The future leaves no such trace. You can only predict it, and predictions are guesses, not memories. From a physical standpoint, a memory is simply information correlated with the past state of a system. When you remember your morning coffee, your neurons are correlating with how that event affected them, how sensory input, smell, and sound altered the chemical structure of your brain. Those changes don't happen in reverse because the underlying physics of heat and energy transfer don't run backward. You can't unboil water, untoast bread, or unremember a memory. Each process has a built-in direction because energy flows from concentrated to dispersed states. Memory is that principle made biological. There's also a beautiful connection between memory and radiation. Just as your brain stores the imprint of experience, the universe itself holds a memory of its own past. The cosmic microwave background, the faint afterglow of the Big Bang. It's literally a record of a time when the cosmos was young and hot, stretched and cooled over billions of years. Every photon from that background carries information about an earlier moment, just as every neuron in your brain carries traces of a previous thought. On every scale, from cosmic to cellular, memory and time point in the same direction, outward, forward, toward higher entropy. But memory isn't just physical, it's emotional. Humans don't just record events, we feel them. Emotion gives memory weight, anchoring it more firmly in our awareness. This, too, is a byproduct of evolution and thermodynamics. Emotionally charged memories trigger stronger chemical responses, reinforcing certain neural pathways while pruning others. Your brain prioritizes what matters for survival: pain, joy, fear, love, and burns energy doing so. The warmth you feel when recalling a happy memory, that's not just metaphorical. Somewhere in your head, microscopic entropy is literally increasing. Interestingly, this emotional dimension also explains why nostalgia feels like both comfort and loss. When you remember something precious, your brain replays the pattern of that memory. But the world around you, and even the neurons storing it, have changed. You're recalling order from a time that no longer exists, contrasting it with the present's greater entropy. Nostalgia is entropy awareness wrapped in sentimentality. It's your biology recognizing that time's arrow has moved on. In a sense, every memory is a fossil of experience. It tells you where you've been, not where you're going. And that's by design. The universe doesn't seem interested in giving us foresight, only hindsight. Perhaps that's because the future is still being written by the constant increase of entropy, one random event at a time. Until it happens, there's nothing to store, nothing to recall, nothing to know. So when you think of memory, don't just think of neurons firing. Think of it as your personal alignment with the cosmic flow of time. Every recollection, from your first heartbreak to the password you can't quite recall, is a small thermodynamic confirmation that the universe is still unfolding forward. Brains are, in essence, living entropy detectors, cataloging the irreversible, one emotion at a time. We remember the past because it's already disordered. We can't remember the future because it's still under construction. Time, for us, is memory's narrative. And like any good story, it only makes sense when read from beginning to end. If the universe had a "do not enter" sign, it would hang right outside the event horizon of a black hole. On one side, physics behaves politely. On the other, every rule you know about space, time, motion, even logic starts to fold in on itself. The black hole isn't just a place where matter disappears. It's where time itself surrenders. It doesn't flow forward. It collapses inward, spiraling toward an end point so extreme that even the concept of next stops making sense. To understand how bizarre that is, picture time and space as the coordinates of existence. One tells you where you are, the other when you are. Under normal conditions, these two dance together smoothly, forming the flexible stage called spacetime. But in a black hole, Einstein's equations show that the dance becomes a tangle. The gravitational pull is so intense that it distorts spacetime beyond recognition. Space, which usually points outward in all directions, becomes a one-way street leading only inward. Time, which normally moves forward, becomes twisted into that same direction. The result? Inside the event horizon, moving forward in time means moving toward the singularity. It's not just poetic language. In the geometry of a black hole, time and space literally trade roles. Outside, you can move freely through space, but not through time. You can go north or south, but not backward in yesterday. Inside, that flips. Inward becomes as inevitable as tomorrow. No matter what you do, every second that passes drags you closer to the singularity at the center, the point of infinite density where our laws of physics crumble. You can't stop, turn around, or pause. Time isn't flowing anymore. It's collapsing, funneling everything toward the same inescapable moment. From the outside, though, things look stranger still. To a distant observer, watching you fall into a black hole would be like watching a movie that never finishes. You'd appear to slow down as you approach the event horizon, your clock ticking slower and slower due to gravitational time dilation. Light from you would stretch into longer wavelengths, turning redder and dimmer until you seemed frozen in place, a ghostly silhouette hovering forever at the edge. From your own perspective, you'd fall through in seconds. From the outside, you'd never quite make it. The black hole doesn't just swallow matter, it swallows moments. This leads to one of the most haunting realizations in physics. From the viewpoint of the external universe, time stops at the event horizon. It's as if black holes are places where the future never arrives. Every event, every heartbeat, every photon near that edge gets trapped in a kind of temporal amber. The black hole's surface marks not just a boundary in space, but a boundary in experience. For anything unlucky enough to cross it, time ceases to be something you travel through. It becomes something that consumes you. The singularity at the center is even more mind-bending. It's the ultimate end of time, a point where density, curvature, and gravity go to infinity. The equations break down there, not because we lack imagination, but because nature itself refuses to make sense. Physicists sometimes compare it to a computer encountering an error it can't process, a cosmic crash screen. The math simply says, undefined. Inside that point, there's no later, no before, no somewhere. Time, as a meaningful concept, has melted away. And yet, black holes might hold the keys to understanding time's deepest secrets. Because while everything seems lost inside, the information about what fell in may not actually vanish. In the 1970s, Stephen Hawking showed that black holes aren't entirely black. They emit faint radiation, now called Hawking radiation, due to quantum effects near the event horizon. Over unimaginable stretches of time, this radiation allows black holes to slowly evaporate. But here's the paradox. If a black hole eventually disappears, what happens to the information about everything that fell into it? Physics insists information can't be destroyed, but black holes seem to eat it without burping it back up. This information paradox isn't just about data, it's about time. If information about the past truly vanishes, then time itself loses its continuity. Cause and effect crumble. It's like deleting pages from the universe's diary. Some theories suggest the information isn't lost at all. It's somehow encoded on the event horizon, spread out in a kind of two-dimensional record of everything that's ever crossed it. That idea evolved into what's now known as the holographic principle, the mind-bending suggestion that the universe might be a projection of information stored on a cosmic surface. If that's true, then black holes aren't erasing time. They're archiving it in the strangest way possible. Einstein himself was skeptical of such singularities. He thought nature would find a way to avoid them, that some hidden law would prevent space-time from collapsing so completely. But general relativity insists they can exist, and the universe agrees. We've now observed black holes indirectly through gravitational waves, the ripples they create when they collide, and even imaged the shadow of one through the Event Horizon Telescope. These aren't just exotic math tricks, they're real cosmic phenomena. And inside each one lurks a region where time as we understand it ceases to function. Some physicists suspect that deep within, at scales smaller than atoms, quantum mechanics might rescue time from total annihilation. Perhaps space-time doesn't end, but loops or foams into something new. Maybe the singularity isn't a dead end at all, but a gateway, a place where time resets, giving birth to a new universe on the other side. It's speculative, yes, but not impossible. In the grand ledger of physics, impossible has a poor track record. For now, though, black holes remain the universe's ultimate paradox machines. Places where time, space, and reality itself blur into something unrecognizable. They're reminders that the arrow of time, so sturdy elsewhere, can bend until it snaps. At the event horizon, the universe stops playing fair. The rules are suspended, and the concept of moving forward becomes meaningless. Outside, the universe ticks on. Inside, the clock doesn't just stop, it ceases to exist. If time is a river, then a black hole is a waterfall that drops off the edge of everything, where direction dissolves and the future falls into silence. If the universe had a heartbeat, you could feel it pulsing in the expansion of space itself. Every second, galaxies drift farther apart. The cosmic fabric stretches a little thinner, and the rhythm of creation slows, like a record playing just a bit too long. This expansion isn't something happening in the universe. It is the universe. Space itself is growing, and time, inseparably woven into that fabric, is stretching with it. The cosmos is not merely aging, it's physically changing the scale of what distance and duration mean. To understand how this cosmic clock works, we have to rewind, though only conceptually, since nature still doesn't offer a rewind button. After the Big Bang, about 13.8 billion years ago. The universe began as a dense, searing soup of energy. Then it started expanding, cooling, and giving rise to matter, stars, and galaxies. But here's the crucial twist. That expansion never stopped. Even now, the space between galaxies isn't empty, it's growing. The universe isn't like a cluster of galaxies flying through pre-existing space. It's more like the surface of an inflating balloon, where every point is getting farther from every other point because the balloon itself is stretching. Einstein's equations of general relativity predicted this expansion long before anyone observed it. In the 1920s, astronomer Edwin Hubble confirmed it by noticing that the light from distant galaxies was redshifted. Their wavelengths stretched as the galaxies receded from us. The farther away they were, the faster they seemed to be moving. That observation wasn't just a discovery about motion. It was a revelation about time. If space was expanding, then time was unfolding alongside it, carrying every atom, every photon, and every moment farther from the explosive origin that set it all in motion. This cosmic stretching isn't uniform in how we feel it, though. On the grand scale, it defines the universe's tempo. But locally, say, within a galaxy, gravity still binds things together. Stars, planets, and people remain anchored while the cosmic ocean around them swells. Yet, that balance is temporary. Over billions of years, as expansion continues, the distances between gravitational islands, galaxies, clusters, even superclusters, grow so vast that their light can no longer reach each other. The night sky, which now dazzles with billions of stars, will one day dim into a silent blackness. The cosmic clock doesn't just tick, it isolates. What's driving this relentless expansion is something even more mysterious: dark energy. This invisible force, discovered in the late 1990s, acts like a repulsive pressure embedded in space itself. Instead of slowing down, as gravity would suggest, the universe's expansion is accelerating. Every moment, new space is being created faster than before, and with it, time is stretching faster too. The rate at which the cosmic clock ticks isn't constant. It's quickening in a strange, counterintuitive race toward emptiness. Imagine a loaf of raisin bread baking in an oven. The dough is the fabric of space. The raisins are galaxies. As the dough rises, the raisins drift apart. From any raisin's perspective, it looks like all the others are moving away. But it's not because they're zooming through space. It's because space itself is swelling between them. Now, imagine that the dough not only rises, but expands faster and faster the longer it bakes. That's our universe, except it's not warm bread you're smelling. It's the slow chill of eternity. This expansion changes everything about the universe's future. As space grows, energy spreads thinner. Radiation weakens, stars burn out, and galaxies lose contact. The cosmic background temperature, the leftover glow from the Big Bang, was once thousands of degrees. Now, it's a chilly 2.7 Kelvin above absolute zero. The universe's clock doesn't tick like a metronome. It ticks like a slowing pendulum, each swing stretching farther than the last. Time itself feels the pull of expansion. But expansion doesn't just alter the pace of time, it defines it. Cosmologists measure the age of the universe not by counting seconds, but by tracing how fast space has stretched since the beginning. That rate is encoded in something called the Hubble constant, which, fittingly, measures the expansion of the universe per unit of distance. The greater the constant, the faster the cosmic clock is running. Yet, here's the cosmic punchline. Even our best measurements of it don't agree. Different techniques give slightly different answers, suggesting that either our instruments are missing something, or the universe is more complicated than our equations admit. It's as if two watches, both built from perfect physics, tick just a little out of sync. And then there's the philosophical weight of it all. As expansion accelerates, the universe moves toward what's called the cosmic event horizon. There will come a time when distant galaxies recede faster than light can travel. Beyond that boundary, their light and their existence will be forever unreachable. The observable universe will shrink, not because it's collapsing, but because the rest is slipping beyond the limits of time's communication. In that far future, our descendants, if any remain, might look up at a dark sky and believe their galaxy is the only one left. Time will still be moving forward, but the story it tells will have grown quieter, lonelier, and colder. This trajectory gives the concept of time an eerie duality. On one hand, expansion creates time. It gives the universe a timeline, a direction, a narrative from dense beginnings to diffuse endings. On the other, it stretches time so far that meaning itself may fade. When stars stop forming and matter thins to near nothing, the cosmic clock won't stop ticking. It'll just slow into silence. Seconds will lose significance when there's nothing left to change. You could say the universe is aging the way glass cools, imperceptibly, but inevitably. The expansion isn't violent. It's graceful, relentless, and indifferent. It doesn't destroy, it dilutes. Every tick of cosmic time pulls galaxies farther apart and energy into ever lower frequencies, like a song fading into static. The universe began as a brilliant, compact crescendo. Now, it hums the long, slow note of endurance. So when we talk about time's forward march, remember that it's not just our clocks that move, it's the entire stage beneath them. The cosmos is stretching the definition of now every instant, and with each passing eon, the distance between moments grows wider. One day, when the stars are gone and even light forgets how to travel, time will still be expanding, patiently, pointlessly, across a universe that has run out of witnesses to count the hours. If the universe had a final chapter, it wouldn't be a dramatic explosion or a fiery collapse. It would be a whisper. No fireworks, no cataclysm, just silence, spreading across eternity. This is the ultimate fate known as heat death. The moment when everything that can happen has happened, and all that remains is a vast, perfectly balanced stillness. It's not an apocalypse. It's an expiration date on motion, light, and meaning itself. To understand heat death, we have to revisit entropy, that quiet architect of time's direction. Entropy isn't chaos in the loud, cinematic sense. It's the gradual equalizing of everything. Over cosmic timescales, stars burn their fuel, galaxies fade, and energy diffuses until there are no gradients left to power change. Every process in the universe, from nuclear fusion to your heartbeat, relies on differences. Differences in temperature, density, or energy. When everything becomes uniform, those differences vanish. The universe becomes perfectly dull. Right now, we live in a golden age of contrast. Stars still shine, planets still orbit, and there are still pockets of heat and motion. But fast forward trillions upon trillions of years, and that won't be the case. The stars will go first. They'll burn their hydrogen and helium, collapsing into white dwarfs, neutron stars, or black holes. For a while, the night sky will glitter with faint, dying embers, tiny remnants of once mighty suns. Then, even those will cool. White dwarfs will fade into black dwarfs, cold, invisible relics that no longer emit light. The galaxies that once filled the universe with brilliance will become ghost towns of matter too tired to move. Meanwhile, the expansion of the universe will continue, stretching space until galaxies drift so far apart that they can no longer see one another. The cosmic web will unravel, each island of matter isolated in a sea of nothing. Even gravity, the universe's most persistent matchmaker, will lose its grip. Some black holes will remain, swallowing stray matter and radiating faint whispers of energy through Hawking radiation. But even that won't last. Over unimaginable spans, gusses of time, 10 to the power of 100 years or more. Black holes themselves will evaporate, dissolving into a final mist of radiation. At that point, the universe will have no structure left. No stars, no galaxies, no black holes. Just particles. Photons, shell neutrinos, maybe a few lonely protons, drifting endlessly through a space that's still expanding. The temperature everywhere will be just a fraction of a degree above absolute zero. It's called thermal equilibrium, and it's the great flattening of all differences. Entropy will have reached its maximum possible value, and the arrow of time will lose its meaning. Think about that for a moment. Time, as we know it, depends on change. We sense time's passage because one state gives way to another. Heat flows, motion stops, memories form. But in a universe of perfect sameness, where nothing changes and nothing can, there's no way to tell one moment from the next. The cosmic clock won't stop ticking. It just won't matter. The difference between before and after will disappear because there will be no events to distinguish them. Time will flatten into an endless, undifferentiated now. This isn't the fiery apocalypse many imagine. It's more like a cosmic retirement. The universe, after eons of expansion and activity, will finally run out of work to do. Energy will still exist, but it will be so evenly spread that it can no longer be used to create or destroy, to heat or cool, to build or decay. The cosmos will have achieved what thermodynamics calls maximum entropy, and what poets might call eternal boredom. And yet, there's something oddly poetic about this fate. Every star that burns, every organism that lives, every thought that flickers in a conscious mind, all of them are temporary rebellions against this inevitable equilibrium. We are entropy's most creative loophole, brief pockets of order that arise and dissolve within the great flow toward uniformity. The heat death may be the final destination, but the journey toward it is filled with complexity, structure, and beauty. You could say the universe's entire story is the process of making interesting things on the way to becoming uninteresting forever. Even so, physicists still debate whether this will truly be the end. The universe might not just fade quietly. It could undergo quantum fluctuations even in its final moments. Over infinite timescales, randomness itself might occasionally conspire to form temporary bursts of order, fleeting bubbles of energy or matter appearing and vanishing, like sparks in a cosmic void. In one of these rare fluctuations, a single atom might form. In another, maybe a black hole. And in the strangest possibilities of all, the vacuum could randomly generate a brief, fully formed consciousness, a so-called Boltzmann brain, a momentary mind adrift in endless darkness, wondering absurdly why it exists. But these speculations are mathematical curiosities, not comforting hopes. For all practical purposes, the heat death is the final act. It's the universe's fade-out scene, not with a bang, but with an asymptote, a slow drift into a state where time has nothing left to do. If the early cosmos was a symphony of explosions, expansion, and light, its finale will be a single, infinitely long rest note. In that far, frozen future, space will be vast and empty, but not in the way it once was. It will be saturated with nothingness, a perfectly uniform field of energy, as flat as mathematics allows. There will be no perspective, no direction, no meaning. The universe will still technically exist, but existence without change is indistinguishable from non-existence. The irony of heat death is that it fulfills the universe's most basic tendency to spread out, to share, to balance everything equally. In doing so, it also erases the very structure that made time possible. Entropy doesn't just win. It wins by ending the game entirely. So, yes, the end of time won't be fiery or dramatic. It'll be eerily calm, a cosmic screensaver looping forever, displaying nothing but the faint afterglow of a universe that once burned with galaxies, life, and questions. Time's arrow will have faded, not because it broke, but because it ran out of anywhere to point. We live our lives in one direction: breakfast before lunch, cause before effect, birth before death. It feels so natural that we rarely question it. Time moves forward because, well, it just does. But what if that feeling, the sense of flowing from past to future, isn't built into the universe at all, but into us? What if the passage of time is less a physical law and more a trick of perception, a feature of the human mind trying to make sense of a reality that doesn't actually move at all? Modern physics has a strange relationship with time. On the one hand, we experience it as a flow, an unstoppable current that sweeps us from moment to moment. On the other, many of our best physical theories treat it as something static and eternal. According to Einstein's relativity, time is just another dimension, woven together with space into the fabric of spacetime. In that fabric, all events, past, present, and future, already exist. They don't happen one after another. They are simultaneously, like pages bound in a completed book. You can flip through it, but the story is already there. Physicists call this the block universe model. In it, the cosmos isn't a film reel running in a projector. It's the entire reel itself, from first frame to last. The Big Bang, the rise of life, your reading of this sentence, and the last flicker of the final star, all coexist in one enormous, timeless structure. To the universe, now doesn't mean anything special. The present moment feels real to you only because your consciousness is moving through that block, one slice at a time, like a flashlight sweeping across a frozen landscape. You don't see the whole terrain, you only see the patch lit up by awareness. It's unsettling, but it might explain a lot about our psychological bias. The feeling that time passes could be an artifact of how our brains process information. Neuroscientists have long known that our perception of the present isn't instantaneous. It's stitched together from a short window of experience, roughly a few hundred milliseconds long. Your brain takes a continuous flow of sensory input, compresses it, and serves it to you as a coherent story. In doing so, it creates the illusion of a moving now. Without that internal editor, reality would look more like a slideshow of disconnected frames. Our brains, in essence, are time narrators. They convert raw data into a story with a direction, from memory to anticipation, from before to after. Without that narrative, cause and effect would lose meaning. Imagine if you experienced events out of order, a glass shattering before it's dropped, a word spoken before you hear it. Your mind wouldn't know how to function. The arrow of time might not be fundamental, but for us, it's necessary. We're hardwired to live in linear stories because that's how we survive them. This bias shapes not only our biology, but our emotions. Regret, nostalgia, hope, fear. These are all feelings that depend on believing the past is fixed and the future open. The arrow of time gives our choices weight. If the universe is a timeless block, then every decision you'll ever make already exists, waiting for your consciousness to arrive there. But that doesn't make the moment meaningless. It just reframes freedom as participation rather than control. You're part of the pattern, not the painter of it. Still, there's something disconcerting about imagining the universe as frozen. In that view, time doesn't pass, we do. Every moment of your life, from childhood to old age, is permanently embedded in space-time like beads on a string. You're not moving through time, you're laid out within it. The you of 10 years ago and the you of tomorrow both exist side by side, separated not by movement, but by perspective. The flow of time, then, might just be the flow of awareness along your personal timeline. But what drives that awareness? Why do we feel pulled forward instead of drifting freely across the temporal landscape? Some physicists suggest the arrow of time isn't just psychological, it's statistical. Entropy increases, giving us a gradient that our minds align with. We remember the past because it left traces, patterns, and order that our brains can reconstruct. The future, by contrast, hasn't yet crystallized those traces. To us, that feels like forward motion, but to the universe, it's just the way probability unfolds. Entropy may give direction to the map, but our minds supply the feeling of movement across it. Even language betrays our bias. We talk about time as something we move through, as if it were a river we're swimming in. We look forward to the future and leave the past behind, forgetting that the metaphor might be backwards. Maybe time isn't flowing past us. Maybe we're the ones flowing through space-time, like ripples spreading through an already complete pond. To the pond, every ripple exists simultaneously. It's only from within the wave that motion seems real. This possibility isn't just philosophical, it's strangely comforting. If all moments exist equally, then nothing is ever truly lost. Every laugh, every sunset, every fleeting instant of love or wonder still exists somewhere in space-time, preserved like fossils in the cosmic strata. The past isn't gone, it's simply inaccessible. The future isn't unreal, it's just unreached. And yet, even if time is an illusion, it's an incredibly persuasive one. We can't step outside it to confirm otherwise. And maybe that's the point. Conscious beings like us might be the universe's way of experiencing its own structure, one moment at a time. We give time texture. We assign meaning to before and after, even if, to the cosmos, they're just coordinates. So perhaps the arrow of time is less a law of physics and more a trick of perspective, a human lens focused on an eternal tableau. The universe may not be moving forward at all. It may simply be timeless and complete. But for those of us living inside it, time's illusion is our most intimate reality. It's how we grow, remember, and hope. It's how we make sense of change in a changeless universe. In the end, maybe time doesn't flow past us. We're the ones flowing through it, passengers on a one-way train with no conductor. The tracks are already laid, the destination already written. But as the scenery of existence blurs past, we lean forward anyway, watching, feeling, believing the illusion that we're the ones driving.